All right, good evening, ladies and gentlemen. In this lesson, we're going to be looking at electrochemistry. Now, many of you did electrochemistry last year under the section of redox reactions. So this is basically an extension of redox reactions, but we're looking at the practical uses of redox reactions. So we're specifically looking at taking redox reactions, and in this particular lesson, we're going to be making batteries, okay? Basically the cells, the normal batteries that you'd use to power things. Although ours, the kind that we're going to be talking about, are exceptionally primitive ones. So I want to just quickly start by asking anyone who's already done this section to quickly just give me a thumbs up. If you've already done electrochemistry, quickly give me a thumbs up. All right. From what I can see, the majority of you have not yet done it, which means that my focus in this lesson, as always, I guess, is that I'm not going to be going too fast. We're going to go right back to what you learned, fortunately not grade 10, only in grade 11. So we're going to quickly be going back just a little bit to the grade 11 redox. I'm going to spend about, I think, 15 to 20 minutes on getting oxidation numbers, whether things have been oxidized or reduced. And then we're going to jump straight in with galvanic cells. Now, the first thing that I just quickly wanted to make sure everybody has seen is that I have attached down the side, I've actually attached it in a file in our chat. Some of you got emailed it a little bit, well, not emailed, WhatsApped a little bit earlier today, the redox table. But I sent a sheet that has 3 on 1 sheet. And subsequently to that, it's almost like the universe was sending it to me. One of my colleagues sent me a redox table that's perfect, that fits on just one sheet. And I thought there's no reason not to use that one for today. It fits better and it's easier than looking at this funny thing. So I have attached that. I hope you all can access it. All right, without further ado, we're going to get going with today's lesson. All right, I'm going to start off as I usually do on the whiteboard with the theory. Okay, so let's just quickly get everything going. Okay, that should work. Okay, so we are dealing specifically with the section of electrochemistry. And I'm going to start quickly just to explain to you what part we're in. So if we look at electrochemistry, we're going to be discussing 2 aspects of it. We're going to be discussing voltaic, that looks very wrong, voltaic or galvanic cells. Yeah. Oh, and we're also going to be discussing electrolytic cells. So just so you are aware, both voltaic and galvanic cells mean the same thing. And in one of the later lessons, not this week, maybe if there's a chance, we will do a little bit of on Thursday. My focus, I actually planned in our lesson plan to do voltaic cells for one lesson, then electrolytic for another, just to make sure that we had enough time. But we'll see how we go. These 2 are 2 completely different sections, and in your exam, they're going to be completely different questions. I think this is typically your question 8, and this is typically your question 9. Usually your electrolytic is about 10 to 11 marks, and your voltaic or galvanic is slightly more marks, about 20, I'd say. So we're going to be focusing today on just this aspect, but I need to mention this because later on when people talk about an electrochemical cell, I need you to appreciate that they both are voltaic or galvanic cells as well as electrolytic cells, and they both fall under electrochemical cells. So just to get your terminology right, electrochemical cells is our umbrella, and galvanic and electrolytic fall underneath it, and those are complete opposites. All right, so with us focusing specifically today, we're going to be focusing on galvanic cells. And the principle behind galvanic cells is that we are going to use a galvanic cell to turn chemical energy into electrical energy. Which means basically that we're going to be looking at spontaneous reactions. Now, a spontaneous reaction is one which happens without us needing to put in energy. So, well, extra energy. It's not technically without us putting in energy, it's without us putting in extra energy. So we don't need to heat it up and we don't need to do anything in addition. It happens automatically. All right, so that's just to give you an overview as to where we're coming from. But now, so that I don't lose you too much, I want to go back to redox. Now, hopefully all of you covered the concept of redox reactions in grade 11. And you learned that redox is a word made up from reduction and oxidation. And in a redox reaction, we have a simultaneous oxidation and reduction. Now, when I was at school, and many of you hopefully have been taught this as well, my teacher taught me oil rig, like those things that we stick in the ocean that mine for oil under the ground, oil rig. Can I quickly just ask, whose teacher taught them oil rig? Last year already. Hands up if you've been taught oil rig. Okay. Most of the teachers use it as a really easy, I think the fancy word is mnemonic, to be able to remind you as to how to put all the bits together. So I'm glad so many of you have that. That means that you know already that oxidation is the loss of electrons and you know that reduction is the gain of electrons. Sometimes people get very technical and they say that it's the loss of electrons from a substance and it's the gain of electrons by a substance, but usually you'll still get the marks for these. So the oil stands for oxidation is loss and the rig stands for reduction is gain. So we can always say that in a redox reaction, the important thing is that electrons, sorry, I'm just going to move this, is that electrons are transferred. Okay, so in a redox reaction, the electrons will be transferred from one substance to another. The reason that a redox reaction needs a simultaneous oxidation and reduction is that the thing that's losing the electrons can't just dump them and say, oh, well, there they go, I lose them, I'm just going to throw them out on the sidewalk. That isn't what happens. It has to give the electrons to something else. Similarly, you can't just gain the electrons by kind of grabbing them. You've got to have both substances with one losing and one gaining the electrons. Electrons are not normally just thrown into a solution to remain there. They're transferred from one thing to another. Right, Emmy, I think you have a question. What's your question?
Sorry, ma'am, there was an accident.
No, don't stress. Don't stress. I'm just quickly checking on the chat. Okay, so some of you said that you learned Lioger. Okay, I must be honest, I've never done Lioger. Brandon, can you quickly tell me what that is for? Loss of electrons, gain.
Yeah. So I think it's gain of electrons is reduction and loss of electrons is oxidation.
Okay, all right. Fortunately, you only have to know one of them. So if you haven't yet been taught one, by all means, oil rig tends to work. As long as you can remember that oxidation means we lose electrons and reduction means we gain electrons, then we're all perfectly fine. Please, I'd just like to point something out here that a lot of students don't get. Redox has to do with electrons being transferred. Not so long ago, we dealt with acids and bases, which dealt with protons being transferred. I don't know if any of you have ever considered the significance of the fact that if you transfer protons, that's your acids and bases section. And if you transfer electrons, that's your redox section. I remember when I was at school and I realized that it was one of those little like light bulb moments where I was like, hey, we're looking at both sides of this thing. Please note, Neutrons, we don't go there, they're just there. Okay, that falls technically, neutrons doing things, falls under radioactivity, which isn't in our syllabus at all. So part of the problem that a lot of people have is it's really easy to know if something's oxidized or reduced if you're given the table. And it's really easy to know if something's oxidized or reduced if you're given the half reactions. But if you're not given the table and if you're not given the half reactions, a large number of people really struggle to figure out the oxidation numbers of the different substances. So I would like today to go through the oxidation rules with you as to how we determine the oxidation number of each substance inside a compound. So I'm going to quickly ask anyone who wants to take a screenshot. I know there's not very much up there yet. I will add to it later. In fact, I'm going to see if I can save it and come back to it later. I don't know if it'll let me open it later, but I'm going to try. All right. So if I move on here, we're doing the oxidation rules. I always have this compulsion. When I was at school, I had a teacher who always used to put an extra exclamation mark after it to make it mean something different. I still follow. So our oxidation rules are effectively for us to determine the oxidation numbers of the different elements in a compound. And I'm saying here in a compound, it doesn't technically have to be a compound, but you're going to find that when we're dealing with elements, the oxidation numbers work differently, starting from rule number 1. The oxidation the oxidation number of an element is always 0. So, for example, if I tell you copper and there's no charge on it, its oxidation number is 0. If I tell you hydrogen gas, even though it's diatomic, there's only one type of element that's there, its oxidation number is 0. If I get really fancy and I tell you sulfur 8, because sulfur forms a molecule that's got 8 sulfur atoms, the oxidation number is 0. Was there a question there from somebody? Okay, I must be honest with this particular section. I'm not 100% certain for the IEB students, but I do think it works the same way. I do recall having to cover this the last time I did it. So please just stick with us. I think it's in there. If you want, you can quickly go and Google and check, but I'm pretty sure that you guys do redox and electrochemical cells. In fact, I know you do because you also do electrolytic cells. You do most of the same electrolytic cells as us. So I'm pretty sure you do need to know this. All right, so any substance that's an element always has an oxidation number that's 0. Now, every other rule that I'm going to write down here applies to compounds. So anything that I write down underneath here, I'm assuming we're not dealing with an element. All other rules apply to compounds. Who can tell me what the difference is between an element and a compound? It's a very easy thing to do, but some of you last did it when you were in grade 9, which was a very long time ago. Maybe grade 10. Anyone? Any volunteers? Brave people? Oh gosh, we've got a chemistry exam to do soon. Okay, yes, Tristan? Oh dear, Tristan, I can hardly hear you. Okay, I did see somebody.
Compound combination.
Okay, so it's not technically a combination, but it's made up of 2 or more elements in a fixed ratio. So a compound is 2 or more elements, different elements, obviously, which are bonded together in a fixed ratio. I usually even leave off the fixed ratio because I'm quite happy with it just being bonded. So if I talk about copper sulfate, that's a compound. If I talk about copper oxide, that's a compound. As soon as it's got 2 different elements in it, it's a compound. So most of these rules kind of make it easy to determine the oxidation numbers. So the rule here is group 1, 2, and 3 metals. And please, when I say 1, 2, and 3, some people will say group 1, 2, and 13. I don't mind which way you call it, but these metals will have an oxidation number. I'm going to abbreviate this, oxidation number of +1, +2, and +3 respectively. Yeah. So if I have aluminium oxide, which has the formula Al2O3, in that formula, the aluminium is always going to be 3+, because aluminium is in group 3. Okay. If I'm dealing with magnesium oxide, MgO, the magnesium is in group 2, so it's going to be 2+. Please note, with all of the oxidation numbers, you'll notice that I'm writing them slightly to the right-hand side and slightly above the element. And also you'll notice that I'm writing them as a subscript, a smaller size. Okay, so this could apply to any group 1, 2, and 3 element. If I did sodium chloride and I asked you what's the sodium's always +1. Now, this, of course, is rule 2. Rule number 1 is more important than rule number 2, which means that if I have aluminium on its own, then it's an element and its oxidation number is 0. It only becomes the +3 when it's bonded to something else, okay? Sodium on its own is 0. It only becomes the +1 when it forms part of a compound. This rule where you have the oxidation numbers being 0 is the most misunderstood and forgotten rule, because you guys are so busy focusing on the rest of the rules that you kind of assume that anything that's in group 1 will be +1. You forget that if it's an element, the rules change. Okay, rule number 3, and please, these rules aren't, the order doesn't really matter. They're just rules that exist, as long as you realize that rule number 1 is more important than any other rule. Okay, so group 1, 2, and 3 metals have an oxidation number of +1, +2, and +3. Oxide, which is our oxygen ion, has an oxidation number of -2. So in fact, if I went into here, this oxygen would be -2 because it's an oxide. This would be -2. But because of rule number 1, if it isn't an ion, because it isn't part of a compound and it's just the element, if it's just diatomic oxygen, it would be 0. Okay. Rule number 4, hydrogen, when it's part of a compound, has an oxidation number of +1. Please note there's a small little exception that if we deal with hydride, which you sometimes do, then hydride would be H-1, okay? But I'll explain to you the difference. This is very rare, just so you know, it's not the common thing. So for example, if I did water, H2O, as an example, the hydrogen would be +1, okay? All right, the oxygen we can in fact already cheat. We know from here it's an oxide because it's part of a compound, so that would be -2. I've got to come here and neaten these up just now. Anyone who's getting irritated because I haven't finished them, I do know. Okay, and then rule number 5 says that all halides, which are our halogen ions, and I'm specifically saying halogen ions because they're part of compounds, so they get the charge. If I was just dealing with halogens, like chlorine gas, then it would be a 0. But as soon as I'm dealing with these, I'm talking about examples like fluorine, chlorine, bromine, and iodine. So our halide ions have an oxidation number of -1. So for example, going back to sodium chloride here, that would be -1. All right. So far I've covered that oxygen you often can predict, hydrogen you often can predict, and the halogens you usually can predict. Those are usually the elements that you start assigning oxidation numbers to. After that, what we do is we look at rules 6 and 7, which overlap each other. The rule 6 basically says that the sum of the oxidation numbers for the atoms, I guess, or elements, in a compound, I usually don't, I just say the sum of oxidation numbers in a neutral compound equals 0. And then the last rule says that the sum of the oxidation numbers in a polyatomic ion is equal to the charge on the ion. So let's quickly look at both of these and how they work. So if I've got water here, because it's neutral, I know that the sum of the oxidation numbers must be 0. So what I do here is I actually create a double layer. I sometimes call it a double decker. The first row is the oxidation numbers of each specific element. So hydrogen we already know is +1 because of rule number 4, and oxygen is -2 because of rule number 3 in the order that I put them. But there are 2 hydrogens. So each hydrogen is +1. So overall, hydrogen contributes +2. +2 minus 2 gives me 0. If I ask you what is the oxidation number of hydrogen, you tell me the bottom number, always. So don't get confused. The top number says the total of everything that everything contributes, but you must put in both bits. Okay, just give me 1 second here. Okay, that won't make a noise again. All right. So that is how we get the sum of the oxidation numbers for a neutral compound to be 0. Let's keep looking at the other examples that I've done. Aluminium was +3. There are 2 of them, which makes it +6. I also don't mind too much if you do the plus before the number or the number before the plus. As long as you've got the correct charge and the correct number, it's fine. Over here, there are 3 oxygens. -2 times 3 is -6. And +6 minus 6 sums to 0. +2 minus 2 sums to 0. +1 minus 1 sums to 0. So that rule often allows us to work out the oxidation number of a specific element in a compound where it can change its oxidation numbers. I don't know if any of you remember, but in the D block, your transition metals, you often don't know the oxidation number of a substance. So if I'm talking about copper, copper, when it's in a compound, can form copper 1 and copper 2. And the only way that you'll be able to know if it's copper 1 or copper 2 is by looking at the oxidation numbers. All right. The last rule here was for the polyatomic ions. So I'm just quickly going to do one example of that. So if we look at the example of sulfate, SO4 2-. I look at this now. I don't know any rule for sulfur. It's not down here. Sulfur, just so you know, can have an oxidation number of -2, 0, +4, and +6. All of those are routine oxidation numbers for sulfur. So I'm not going to guess what it is. I'm going to work it out. Oxygen is -2. That comes from this rule. There are 4 of them, which makes it -8. Something -8 equals -2, and the answer is that it is +6. So sulfur in this specific sulfate ion has an oxidation number of +6. Okay, I'm now going to quickly give you a challenge. Maybe we'll do 1 or 2 together as partial challenges, and then I'm going to quickly give you an activity for all of you to try. So if we look at NO3 minus, this is also where it's important that you know the oxidation numbers of your entire polyatomic ions. I'm going to ask you to quickly work out what nitrogen is. So if you want to work faster than me, that's what we're working on. So you can work at your own pace. I'm going to go through this one slowly. Oxygen, because it's part of a compound or a polyatomic ion, is -2. There are 3 of them, which makes it -6. Something -6 gives me -1. So my nitrogen in this case is +5. All right. Please, can I ask you to quickly take a screenshot if you need to before I pause and we get started on the next bit. All right. Okay, sorry, there was a question there. Could I quickly explain sulfur again with pleasure? Okay, so if I go back to the sulfate ion, oxygen is -2. Because of the 4, which says that there's 4 oxygens and 1 sulfur in the ion, because of the 4, it's 4 times the -2 gives me -8. If the overall charge is -2, 6 of the negatives from here must have been cancelled out with the charge from the sulfur, so sulfur must be +6. So +6 minus 8 gives me -2, or 2 minus. Okay, it doesn't really matter which way around you look at it from. So over here, sometimes I find that it's good to actually use algebra, where you can go and say this one's x, and then I'd go and say x minus 8 equals -2, and then the x would equal -2 plus 8, which is +6. Please also remember that your oxidation numbers must have a charge. Okay. The rule 6 simply says that if you've got a neutral compound, all of the oxidation numbers will sum to 0. So, okay, let's do a nasty one that involves sulfate. If I have H2, in fact, I'll make it difficult. I'll make it sulfite. I hope you all know that sulfate is the SO4 2 minus, and sulfite is the SO3 2 minus. So, if I look over here, I can use a rule for hydrogen and oxygens that I can work out sulfur. Hydrogen is +1. There are 2 of them, so hydrogen as a whole contributes 2 positives to the charge. Basically, what this positive means is that in this molecule that forms, hydrogen overall will give away 2 electrons. Kind of explains how it shares its electrons, whether it gains the electrons more or loses them more. Now, I don't want you for a second, please don't get confused here, because a lot of people at this point will go, but man, this is covalent bonding, it's all sharing. Yes, it is all sharing like that, but this is how the balancing works in terms of oxidation numbers. So we can kind of imagine if something's positive, that it's tending overall for hydrogen to have a tendency to lose the electrons here. Okay, please don't actually think of it as gaining and losing electrons. That just makes it nasty. So it has to do with the how it works in terms of becoming stable. Okay, so over here hydrogen would tend to have shared 1 away. Okay, our oxygen is -2. There are 3 of them, so it's -6. So what must the sulfur be in this case? Okay, don't worry about not understanding the 4 bit in brackets. I'll get to that just now. Okay, so what must sulfur have been here? So I'd say +2 plus x equals -6. If I take this, no, that doesn't work. Sorry, doesn't equal -6. That's why I'm getting myself confused. It equals 0 because it's neutral. So this is going to be +2 plus x minus 6 equals 0. Suddenly looking at it going, nothing gets you -8. So over here, we're going to have +2 minus 6. Okay, means we're going to have that x minus 4 is 0. If we take the x over to the other side, we get x is 4. And if you change that and put in a +4, +2 plus 4 gives you +6 minus 6. The sum of all of these numbers is equal to 0 because it's neutral. Now, ladies and gentlemen, if you've never done this before, and if you've never understood it before, it should have been done in grade 11, but sometimes it isn't covered as a priority. Sometimes people jump straight into let's do redox without realizing that you can't do redox if you don't actually understand how to identify if something has been oxidized or reduced. For anybody that feels like I'm beginning to lose you, I promise this all makes sense in just a minute. So please quickly take a screenshot. I did suggest that a little while ago while I quickly save and then clear all the drawings. Okay, now I wanted to just start. I'm going back to look at all of you. Who here has already done oxidation numbers? Or remembers them from a previous grade? Let's be broad here. Okay, so it looks like for the majority of you, oxidation numbers is a relatively foreign concept. Now, it's very important that you do understand oxidation numbers because it is possible in the matric exam that they test you on oxygen and the oxidation equation isn't on your table. So it's fine for most questions that you don't understand what I'm doing. But when they do throw in questions where you have to know it, you're going to end up being completely lost. So that's why I always cover it. All right, Bella, was there a question?
No, sorry. My computer's just very confusing with Zoom. I don't know why. I've always had issues with it.
Don't
So,
stress.
sorry.
Hello. Thank you for joining us. All right. So if I'm looking at examples, I always find a lot of people struggle with this idea until we actually start practicing it. So I'm going to pick some rather nasty examples to show you what we're doing. So if I look at KMNO4, KMNO4 is potassium permanganate. And I asked you, what is the oxidation number of manganese? You'd have to use some of the rules that we came up with. The oxidation number of potassium, who can tell me what potassium is? Using the rules that we had written down before. I'll give you a hint. Potassium is a metal in group 1. So it's a group 1 metal. Potassium is going to be +1. All right, yay, I did have someone getting it right. And oxygen here is going to be -2, but there are 4 of them, so that makes it -8. Who can tell me from this what manganese is going to be in the potassium permanganate compound? Technically, it's not, yeah, it's a bit, we'll call it the formula unit. Any ideas? Come on, do the maths backwards. Okay, I've got a good couple of answers and we've all got +7, so let's see if that works. So if I make this +7, +1 +7 gives me +8, -8 gives me 0, and because there's no charge on it, this makes perfect sense. All right, okay, so you've got to just be careful about doing your maths. Next example, what about if I do SO2, which is sulfur, I'm doing it with the pH today, but please, it is technically with an F, sulfur dioxide. Now, the first thing I need to point out, and a lot of you get very confused, there is a difference between SO3 and SO3 2-, okay? SO3 is called sulfur, and I'm jumping a little bit here, but this is called sulfur trioxide, and this is called sulfite. I'm going to show you in just a second how these two are different, but we're going to go back to sulfur here. What is the oxidation number of oxygen? Hopefully you all know by now, it's -2 because it's in a compound. And if there are 2 of them, -4. Because this has an overall oxidation number of 0 because it's neutral, this must be +4. All right, so that's how this one works, okay? Next one over here, oxygen is -2. There are 3 of them, makes it -6. This sulfur is going to be +6. So I told you sulfur can be +6 and +4. Over here, the oxygen is -2. There are 3 of them, so it's -6. But here it's something -6 gives me -2. Please, it doesn't matter which way around these go. You'll notice I swap them around sometimes in my thinking as well. But if we have something -6 gives me -2, that becomes +4. Now, I mentioned the example of a hydride earlier. That is because if I have the H at the end of a molecule after a cation, then what happens is this is no longer viewed as being hydrogen. This is specifically a hydride. And when it is a hydride, the rule follows that sodium is +1 because it's in group 1. And because these must sum to 0, the hydrogen becomes -1. So the only time that hydrogen will be -1 instead of +1 is if it's given with a cation obviously in front of it, and that means that it would usually be at the end of the name. Okay, it's an exception, so don't panic too much about it. All right, somebody said, what about hydroxide? Hydroxide is a polyatomic ion, so the sum of all of the oxidation numbers must be -1. Oxygen is -2, hydrogen is +1. -2 + 1 gives me -1. Hydroxide is a polyatomic ion. Its oxidation numbers make sense. All right. Is this beginning to make a little bit more sense to everybody here? So So I'm just going to quickly pause sharing for just a second. Can I ask who's beginning to get the sense that they kind of understand how the numbers fit together? Okay, it does take a bit of practice, but usually the reason it's so important is we give you one of the weird, freaky ones, and then we suddenly go, ooh, what's the oxidation number of chromium or of manganese? And then you freak out. So I'm going to do just one last check with you before we actually start linking this all to what we're going to do most of our testing on. All right, so I did potassium permanganate at the beginning. I'm now going to do K2Cr2O7. This is known as potassium dichromate. Now, I want you, even though this looks big and scary, to take it apart bit by bit like I've done the rest of them. You have a rule to work out what potassium is. You have a rule to work out what oxygen is. Can I ask everybody to quickly try and work out for themselves what the chromium is? All right, so I'm going to quickly pause my sharing. So quickly see if you can figure it out. When you've done it, you can give me a thumbs up and we'll work from there. Okay, it's not plus 12. Okay, good. Some of you have already got there. Good. Okay, fantastic. Okay, the numbers that I'm seeing that people are sending out look like the right ones, which is a good sign. Okay, it's not plus 16. All right, so I'm going to resume sharing. Sorry for anyone who thought I was going to give you the answer. I'm going to work through it with you still. So potassium is in group 1, so it's plus 1. There are 2 of them, so double decker makes it plus 2. Always get used to this idea of double decker and remember that the number that you write at the bottom is its actual oxidation number. The number you write at the top is what all of the atoms of that element contribute to the molecule. Oxygen here is -2. There are 7 of them, so it's -14. So we could do a little bit of maths here, saying plus 2 plus x minus 14 equals 0 because it's neutral. So therefore, if you work this out, we can get that x is equal to 14 minus 2, which yay gives us 12. But the 12 is the top number. There are 2 of them, so each one is only +6. All right. Now, the good news is, if you could do that one, that is as hard as it gets, okay? This is the hardest one that I usually come across. There are a couple of quick exceptions, and I'd like to just cover the exceptions that I don't have a feeling later on that I've kind of neglected to give you all of the information that you need. So I'm just quickly going to do the weird exceptions that pop up. I've already done one of them, which is a hydride. Please don't jump to the assumption it's a hydride. This is kind of 1 in 100. The other one that sometimes comes up is if we've got an example like H2O2, hydrogen peroxide, okay? So the other exception that we have deals specifically with oxygen changing, and it's when we deal with it as a peroxide, okay? So our assumption here is hydrogen is +1. There are 2 of them, makes it +2. If this is overall neutral, oxygen must be -2, but there are 2 of them, so each is only -1. So remember, a hydride is going to have an oxidation number of -1, and a peroxide has an oxidation number of -1. But once again, these 2 are your exceptions, not your rules. So if you, every single time you see it, assume, oh my gosh, it's a peroxide, you're just going to mess up on your oxygens. So I would almost suggest, sometimes I don't even teach these 2 because the chances of them coming up are so slim. And if they do come up, you're going to use your table to do them anyway. Okay, so I'm going to quickly clear this, and we're going to go back to the idea that we started at right at the beginning, looking at redox. Okay, so if I look at magnesium and I react it with oxygen, I will form magnesium oxide. Please, you are in matric. At this point, you need to know that magnesium is Mg2+ and O2-. You need to know and not make up weird formulas for what it is, okay? So we've got a formula here that says magnesium plus oxygen gives me magnesium oxide. This is not balanced. In order to balance it, I must put a 2 there and I must put a 2 there. Now I'm going to ask all of you at home to quickly write this down, and then I'd like you to write in the oxidation number of magnesium, oxygen, magnesium, and the oxide. Quickly do that for me. When you're done, you can give me a thumbs up so that I know you're ready to continue. Okay, good. Okay. It's looking like more than half of you at least. Okay, so I'm going to quickly fill you in here. I'm interested to see how many people got this completely correct. Magnesium is 0. Oxygen is 0 because they're both elements. Magnesium is +2 or 2+, and oxygen is -2 or 2-. Can I quickly ask for a show of hands who got that completely correct? Some of you have the hidden advantage that this is the only example I ever start with because it's nice and easy. But there's a reason that I start with this example. I want us to look at the idea of redox. We're now going to go and look at what we started with at the very beginning, which is oil rig. Oxidation is loss of electrons and reduction is gain of electrons. If magnesium starts with a number of 0 and goes to a number of 2+, it has lost 2 electrons, okay? Because electrons are negative, and when you lose negative electrons, your oxidation number becomes more positive. If we look at oxygen, oxygen has gone from 0 to 2-, so it has gained negative electrons, okay? And we're not even going to specify exactly how many electrons it's gained. This is a redox reaction. In fact, in a redox reaction, this particular example, every single substance changed its oxidation number. That isn't always guaranteed to be the case. Sometimes it is, sometimes it isn't. So we're going to be speaking in this case about an oxidation half reaction. OHR is an oxidation half reaction and a reduction half reaction. Now, usually what I'm about to do now is something that we make you do in grade 11 because it's good practice, but in grade 12, you usually don't have to do it. The only exception in grade 12 that you do need to be able to do it with is this exact example that I'm about to do with oxygen, because oxygen isn't in your table. So you're never going to be able to look oxygen up in your table. The only way you can ever do oxygen is if you've got it in your head and you can figure it out like I'm about to show you now. So for my oxidation half reaction, oxidation is loss, okay? This is my oxidation half reaction. Magnesium is going to lose 2 electrons. This is my reduction half reaction. Oxygen is going to gain 2 electrons. So let's start with my oxidation half reaction. We start with magnesium and we finish with magnesium 2+. Now, if it loses 2 electrons, we don't write -2 electrons. This is not maths, this is science. So if we lose 2 electrons, those 2 electrons are part of our product. We only ever write electrons as a positive, so it's ever plus however many electrons. We know that it's 2 electrons because the charge becomes +2. Okay, so that is our oxidation half reaction. Our reduction half reaction gets a little bit more complicated, and I don't know why I'm writing that. Our reduction half reaction starts with oxygen, and it goes to O2-. Now, this is where it gets a bit confusing. Oxygen is diatomic, so it's got 2 oxygen atoms. So from it, we must make 2 oxygen ions. Each of those oxygen ions needs 2 electrons, so we actually have to pick up a total of 4 electrons, okay? Quite often in your matric exam, you'll be able to look up your oxidation and your reduction half reaction from your table. But as I've already mentioned numerous times, this reaction is not on it. Okay, so you've got to be ready for the idea that you need to be able to memorize this or figure it out. So quite often we ask you for the oxidation half reaction, the reduction half reaction, and then the last thing that we commonly ask you for, and this will apply whether you look up these two half reactions on the table or not, is called the Net Ionic Equation. Now, when I was at school, we were unlucky enough that we were expected to, in addition to the Net Ionic Equation, add spectator ions back in. When they changed the syllabus, they took needing to put spectator ions back in out. So you no longer need to be able to put spectator ions in. So I'm not going to show you anything with spectator ions. We're just going to ignore them. So the way you work out your net ionic equation is you first of all make sure that the number of electrons lost and gained are equal. The lowest common multiple of 2 and 4 is 4. So 4 electrons are going to need to be transferred. In order to get this to 4 electrons, I must times everything here by 2, which means I put a 2 in front of the magnesium, a 2 in front of the magnesium 2 plus, and change this to a 4. I also am now going to add everything here that comes before either arrow, and then everything here after the arrow. I'm going to do this quickly with the values in that I normally leave out because I'm not going to be lazy. But here we'd have 2 magnesiums, there it is, plus oxygen, plus 4 electrons. I normally don't write the electrons in because I know they're going to cancel on both sides. I'm just quickly showing you. Over here, we'd then have 2 magnesium, 2 pluses, and 2 oxide ions. Please note, these are going to combine together. If you've got a positive and a negative ion, they can combine together, and we can change these to be 2MgO, which is exactly what I've got over there. So I'm showing you one of the ways that we can get to that rule, but sometimes they just give you the oxidation and the reduction half, and then you need to do the net ionic from that. So over here, you can leave this either as those two, or more commonly, we combine them together to make the compound. All right. Can I quickly ask, who found that what I've just done kind of made a little bit of sense as to why we cared about oxidation numbers? Okay, because if we completely ignore the oxidation numbers, things actually get a little bit confusing on certain examples. So I'm going to, we've got 2 weeks to go over this section. I don't want to leave you hanging where I just kind of give you a little bit of information and then rush through and you can't do it nicely in an exam. All right, so I've got another question for you. I'm going to challenge you, and I'm not going to make you do the OHR and the RHR because it's a lot of work. I want you just to identify your oxidation and your reduction half reaction, and then I'm going to introduce you to the table and show you that I've actually made you do this a really hard way, but the reason, as I've mentioned, that I do it is there are a few exceptions where you will need to do it and you don't have a cheat shortcut. So I would like everybody here right now to work out for me if H2S reacts with SO2 to produce sulfur and water. Please note, none of this is balanced. It's not meant to be balanced. I'll balance it later once I found my OHR and my RHR. So for now, I just quickly want everybody to write just the oxidation numbers for this particular equation. All right, give me a thumbs up when you've done that. Okay. Okay, wonderful. All right, that looks like most of you are done. I think we've done enough practice here, so I'm just going to jump straight into the answer. Can I ask, showing you this answer here, who's got the same answer as me? Let me just quickly check that I didn't make a mistake. No, I didn't make a mistake. We're good. Whew. All right. Suddenly, as I was showing it to you, I thought, very few of you that got the same answer as me. Maybe I messed up here. All right. So if I go back to what I've got here, hydrogen is +1. There are 2 of them makes it +2. +2 -2 for this to be 0. -2, 2 of them is -4. They must be the same, but opposite signs in order for it to be 0. Sulfur is an element which makes it 0. Okay. Hydrogen is +1, but there are 2 of them. Oxygen is -2, and those once again are 0. Now, tricky bit. If you look closely at this, you will see that hydrogen goes from being +1 to being +1. It has not changed its oxidation number, which means that in this case, H+ is a spectator ion. If something does not change its oxidation number, it's a spectator ion. It's sitting and it's watching. It's not actually participating. The next thing is oxygen goes from -2 to -2. Oxygen is also a spectator ion. Spectator ions do not change their oxidation numbers. Which means that we end up with a rare situation here where sulfur is the product of both oxidation and reduction. So if we go from S2-, which is called sulfide, to sulfur 0, this must have gained electrons. And if it gains electrons, it is therefore reduced. Okay, I know some of you think I'm doing this very slowly because I'm trying to help you. I must be honest, I cannot go from gaining electrons straight to the answer. I actually can't go from here to here and see that it's reduced without saying gained electrons. It's just been the way I've always learned this. And sulfur here goes from +4 to 0, which means it's gone from a positive to 0. So wait, no, did that the wrong way around. Told you I couldn't think it through. If we go from negative to 0, if we go from negative to 0, we have lost negative electrons. I didn't see any of you ask that question or pick that up, so I guess I'm still teaching you. That's a good thing. So if we go from -2 to 0, we've actually lost negatives. Okay, we become more positive. So lost electrons, that is oxidized. My bad. And if we go from +4 to 0, we have gained negatives. And since we've gained electrons, we are therefore reduced. So in this case, sulfur is the product of both the oxidation of sulfur 2- and the reduction of sulfur 4+. Now, for us to write out an OHR and an RHR here gets virtually impossible, because you're suddenly dealing with the fact that what do we do with the hydrogens and the oxygens? And are we dealing with the S2- or are we dealing with the S4? Oh, it's messy. So instead, ladies and gentlemen, I'm going to show you the easy way to do this. And fortunately from there, it's really nice. Okay, so I'm going to quickly stop sharing that bit. I'm going to put on my table and then I'm going to share across again. All right. So if I share my screen, wrong screen. If I share my screen, you all should see the redox table that you hopefully were introduced to last year. Now, ladies and gentlemen, I'm probably going to end up getting eaten alive for this, but with this table, I'm going to strongly recommend that you only ever use the table 4B, okay? I am aware of the fact, I think it's Edgemead. Edgemead uses table 4A, and I only know this because one of my friends that I mark with is a teacher at Edgemead, and we were discussing it the one day, and I said, I don't even know why they published table 4A and nobody uses the table 4A. She said, we do. And I said, how do you use it? Because I've never known how. So at the top of the table, you would have seen that this said 4B. Everything that I'm about to teach you is for table 4B. If you pick the wrong table in the exam and you use 4A, none of what I've told you will work. If you are a student who goes to Edgemead, by all means, you can listen to both options and decide which one you want to work with. But I must be honest, I still don't know how table 4a works. Basically, table 4a is the exact same table, but it's the other way around, kind of. So I recommend in an exams that you don't use the wrong question. Make sure you find 4a, pencil and ruler, draw a cross across it so that you don't accidentally flip back to it by mistake. Now, this table is provided in your exam, and it has all of the different reactions that you need to know. So if you look carefully at this table, you will notice that the electrons are only on this side. This is very important. You'll also notice that every single reaction here is written with a double-sided arrow. That means that we can read that reaction from right to left, okay, from right to left, or from left to right. We can read every single reaction both ways. So let me randomly pick on one. I'm going to pick on the reaction that I've got right at the top, which is lithium. If I read it from right to left, this way around, then I will see that I get lithium going to lithium plus an electron. Please note, even if you change the order and you say the electron and lithium afterwards, it doesn't matter. If you read it this way around, it will be your oxidation half reaction, because oxidation is loss and your electrons are your products. So whenever you read a reaction on the table 4b, from right to left, you are reading an oxidation half reaction. Whenever you read a reaction on the table from left to right, you will be reading the reduction half reaction because you will be gaining electrons. So if I read the same reaction this way, it is now a reduction. So any reaction here can be read as either an oxidation or a reduction. For me, what determines which way round you read it depends on what your starting materials are. All right, so I'm just quickly going to clear here so that I can keep writing. So what I showed you in the previous question was that we had a reaction where we had H2S and we had SO2. So when I'm going to go and find those substances, I have a bit of a cheat advantage. I know where they are. There's sulfur dioxide. There's another sulfur dioxide we have to choose. And H2S is over there. Now, please note, if you only have H2S on the right-hand side, and it has to be your starting material, it can only be read that way around. I know I've just scribbled over it to write it, but the point is it can only be read that way around. That way around is your oxidation half reaction. So anything that we read from right to left automatically is our OHR. So here my oxidation half reaction says hydrogen sulfide reacts to give me sulfur plus 2H plus 2 electrons, okay? Now we have a choice of sulfur dioxides. You often are going to find that there are different compounds here which appear on both sides, and you have to make a choice. If you look for water here, there's a water there. There are about 4 waters. There's a water there, maybe not quite so many. I'll find another one that's hydrogen peroxide. There's a water, there's a water. We get all sorts of waters. So you've got to make sure that you pick the right equation with the substance in it. Don't just randomly guess. Now, if this is oxidized and it loses electrons, it's not going to react with something else that is also being oxidized. There's no point in that going that way, because then we've got 2 things which are both giving away electrons and no reaction happens. So we are not going to use that reaction. We will pick something that loses electrons and something that gains electrons. So over here, my reduction half reaction for this particular reaction will be SO2 plus 4H plus 4 electrons goes to give me sulfur plus, that's not going to show so well, so I'll redo it here, sulfur plus 2H2O. Okay, so over here, that is my oxidation half reaction. That is my reduction half reaction. Much easier to find it on a table. It does take practice to find the correct version of it, but it's not that impossible. Okay, so we've got our OHR and we've got our RHR. From here, we're also going to practice doing our net ionic. Now, the net ionic, if you remember, involved us starting by getting the correct number of electrons on both. if this is 2 and this is 4, everything here gets times by 2. So I'm going to put a 2 there, change that to a 4, change that to a 4, change that to a 2. And if I now write out my net ionic, and I'm going to not rewrite the electrons, I have, I'm hoping this shows up nicely, 2H2S plus. Now we've already hit the arrow here, so I move on to the next equation. SO2 plus 4H plus. I'm not writing out the 4 electrons, they're going to cancel with each other. Goes to give me 2S plus 4H plus, okay, plus sulfur plus 2H2O. I'm sorry if you can't read that very neatly. So next line, I think I'm going to do in black, hopefully you can see. This 4H plus and this 4H plus are on either sides of the arrow, so they cancel out. 2 sulfurs plus a sulfur, they add together to give me 3 sulfurs. And my overall equation is 2H2S plus SO2 goes to give me 3 sulfurs plus 2H2O. That is a slightly tricky example, kind of reminiscent of what you mainly did in grade 11, but hopefully it's starting to make a little bit more sense, as well as it's making a little bit of sense as to how you use the table. Now, those ideas are kind of where we're going to be establishing things. And what I want to do in the last half an hour today is I actually want to start building cells with you. But this is the important work that you should have built up from grade 11 in order to be able to do this section in grade 12. All right. Nope, there's no rule here about multiplying the OHR by 2 and doing nothing for the bottom one. You have to look at how many electrons are being lost or gained. It's just by chance that I happen to have picked 2 examples that work that way. All right, so please don't make any rules that are not 100% clear all of the time. All right, ladies and gentlemen, we're about halfway, just over halfway through the lesson. I kind of went a bit over. Can I ask everyone just quickly to stretch? Because the bit that we're now moving on to is the main bit that you're going to get examined on in matric. So I'm going to quickly ask you to just stand up. Have like a quick run to the bathroom. And then we're going to get started on how we actually turn this reaction into making a cell. All right, I can see someone who's actually run to the bathroom, so I think I'm going to give you guys a fair chance. There we go. All right. Okay, so when we deal with the reactions here where we're actually going to try and make a cell, the important thing from a cell is that we need a spontaneous reaction. I'm also just going to cover a little bit more ideas, or a few more ideas with you with regards to anodes, cathodes, oxidizing and reducing agents. All right, so let me get back and share the screen. Okay. So I find that this is probably the easiest way to teach this section, so you're going to have to bear with me. If you disagree with me, you can come back later. When we construct a voltaic cell must contain a spontaneous reaction. There's no point in making a battery if the battery won't actually produce energy. So the way that we do this is we have a solid piece that can conduct electricity. A solid that can conduct electricity we call an electrode. And we place an electrode, and this electrode is then connected to a voltmeter. Doesn't necessarily have to be a voltmeter, but it could be connected to a voltmeter or to an ammeter or to a galvanometer. In fact, the voltaic comes from the fact that we get a voltmeter reading, and the word galvanic comes from the fact that we get a galvanometer reading. So effectively, what we're going to do here is we're hoping to produce electricity that registers on a voltmeter. And then on the other side, we're also going to have another electrode. And what we're going to try and do is convince electrons to move from one electrode to another through a voltmeter to another electrode through a spontaneous reaction. We have 2 half cells where we effectively have an electrode, usually in its own electrolyte. So important ideas, an electrode is a solid, an electrolyte is usually an aqueous solution that can conduct electricity. Important thing, electrode conducts electricity and it's a solid, electrolyte conducts electricity. And the reason that we do both an electrode and an electrolyte that effectively give us both sides of the half reaction is that we can guarantee that they'll be spontaneous. So I'm going to pick on an example that I don't usually pick on because I know that most of you will start with zinc and copper, and I want to do something a little bit different. So what I'm going to start with today is I'm going to start with silver in silver plus. And I'm going to start, we may as well, with copper in copper 2 plus. So basically, if you look at this, we usually have an electrode in its own electrolyte. There are a few exceptions where it doesn't look exactly like this, but most of them are relatively similar. Now, what I'm going to show you is when you get given a cell like this, and you're not always going to be given it this way, sometimes you're given it from the backward side, is you're going to go and look for the silver and the silver plus and the copper 2 plus on your table of your table of cell potentials. So if I go over here, I'm now going to quickly share with you, and we're going to go back to this table. So if you remember, and I'm cheating here, I know that many of you do not know this table quite as well as I do. Please don't panic if it takes you a little bit longer to look things up. But over here, I have silver and I have silver plus. And then the other one that I looked for was copper and copper 2 plus. There's copper 2 plus. Now, the reason that we always have everything that you need from both sides is that we want a spontaneous reaction to occur. Now, if you look down the left and right-hand sides of your table, you will see that it says increasing reducing ability. That means that as we go up the substances on the right-hand side of the table, the closer we get to the top, the better these substances are as acting as reducing agents. I'm going to describe what a reducing agent is for you just now. As we go down the table, we see that we have a better oxidizing ability, which means that the substances on the left-hand side are all oxidizing agents. And the closer we get to the bottom, the better they are at being an oxidizing agent. Now, I have neglected to tell you what a reducing agent is and an oxidizing agent is, but some of you may even remember this from last year. The important thing that you need to know is that a reducing agent is a substance that is oxidized. It does exactly the opposite of its name, or exactly the opposite of its name happens to it. So basically, a reducing agent causes something else to be reduced when it is oxidized. Oxidation is loss of electrons. So if a reducing agent loses electrons, it gives those electrons to another substance. And because that other substance can then gain electrons, that other substance is reduced. So the opposite happens to the substance. So if we ever put in the word agent, the opposite happens. So if something is a beta reducing agent, that means that it will be selectively means as preference, it will be selectively oxidized. That means that the closer a substance on the right-hand side is to the top, the more likely it is to be oxidized. Okay, going back to the idea here about an oxidizing agent. An oxidizing agent is a substance that is reduced. Okay, so the better a substance is as an oxidizing agent, the more likely it is to be selectively oxidized. Reduced, wrong word. So I always tell my students that for this to be spontaneous, you will have your oxidation half reaction, a above your reduction half reaction. The thing that wants to lose electrons will spontaneously lose electrons, and the thing that wants to gain electrons will spontaneously gain electrons. So if we look at our example here with copper, copper 2 plus, and silver, silver 2 plus, in order for this to be spontaneous, it makes logical sense that copper will be oxidized to copper 2 plus if we want it to be spontaneous, and silver will be reduced to silver plus. I hope that this makes sense to everybody here. So if this reaction is spontaneous, then we know, because we've got both sides, we could read it as oxidation or reduction, but in order for it to happen spontaneously and give off energy, it's got to go this way around. So our oxidation half reaction is that copper will go to copper 2 plus and give off 2 electrons, and our reduction half reaction here is that silver plus will pick up an electron and go to silver. Okay, now because I want to do a lot of stuff in the same time over here, I'm just quickly going to throw you guys in the deep end. I promise that everything I say now, I will come back to and I will clarify in a bit more detail, but I want, while I've got it all on one table, to quickly show you a couple of the things that I normally only go to later. Okay, so please just bear with me. I am asking very nicely, otherwise you're going to get lost later. So if we've got this battery cell, it's got to produce a voltage that we'll read on our voltmeter. And we can actually work out how big that voltage is by using these E theta values down the side of the table. You will notice that hydrogen has a value of 0. That is because everything is compared to its ability to oxidize or reduce hydrogen and H+. Okay, so everything has its value, its E theta cell value, E theta half cell value compared to the hydrogen reaction. If you look on your formula sheet, you will see that there are 3 equations to work out the E theta cell, which is literally the voltage of the cell that you're going to get under certain conditions. And for us to work this out, you will see that they specifically say that it's E theta reduction minus E theta oxidation. So the voltage reading that we're going to get if the cell is performed at certain conditions will be the reduction value. Now please remember, this was my oxidation half reaction. This is my reduction half reaction. So if I go and look in here, it will be positive 0.80 minus, okay, you can see that there's a minus there. If we go up to here, we'll see that this is 0.34. If you want, you can put in the positive as well, but we don't really have to. So if we've got 0.8 minus 0.34, we can actually ahead of time say that this is going to have a value of 0.46 volts. Okay, so it is possible for us with this table ahead of time to actually work out a whole bunch of things. The voltage, we've got a special shorthand that we use to write down the reaction called a cell notation, etc. But before we go too much further, I'd like to pause. I'm going to go back to what I was showing you earlier, and hopefully that will all make sense and it won't get too lost. So I'm just going to quickly make a little note for myself what my 2 half reactions are so that I don't lose out on everything that I was talking about here. Okay. All right, so if I now go back to what I was originally looking at here, what we hopefully would have got from the previous page was that my oxidation half reaction was copper goes to copper 2 plus 2 electrons, and for my reduction half reaction, that silver plus picks up an electron and turns into silver. What? Did I get that right? Sorry, just give me 1 second, everybody. I'm coming back. I'm just suddenly looking at it and going, that doesn't make sense in terms of what is happening. Copper goes to copper 2 plus, And Ag plus goes to Ag. Oh, that does. Sorry, I'm being very, very silly here. I was suddenly thinking about electroplating and thinking that it didn't work, but it does work. Okay. I have too much experience trying to make this reaction work when it doesn't want to for me. So what this means is that the copper will turn into copper 2+. What this physically will look like is our copper electrode is going to dissolve into solution. So I'm going to quickly take away the outside of the electrode to show you what will happen over time. Is over time, the top half will have nothing happen to it, but the bottom half will get small and skinny because the copper has turned into copper 2+ ions. Also, what will happen here is as we make more and more copper 2+ ions, the solution at the bottom will become more and more blue in color because the copper 2+ ion, actually that's a better blue, copper 2+ ion is blue. So copper turns into copper 2+. Okay, I'm also going to just quickly make the copper look orange. There we go. What happens on the other side is that if you look here, silver plus turns into silver. So this silver will deposit on top of the other silver. And because it's depositing, you'll notice I only draw the lines under the water level, the electrolyte level. But we're going to end up with a layer of silver depositing on here. Now, there were a couple of things that I raced through that I didn't quite mention. So if you remember, I started with the idea of oil rig, where oxidation is loss of electrons, reduction is gain. And then I mentioned to you that if a substance is oxidized, then we call it the reducing agent. And if a substance is reduced, then we call it the oxidizing agent. There is one last word rhyme like this that you need to remember. And it's a bit of a weird one. I don't think any other teachers teach this one, but it's just the one that I learned when I was younger, is anox and red cat. Can I ask just quickly, has anyone else done anox and red cat? Oh, wow. Okay, so it's more of you than I thought. Wow. All right. Okay. I wonder if anybody else's teachers explain it quite as inappropriately as I do. All right. So the way that I view this is our easiest way to know which electrode is which. We give special names to our electrodes, and we call the anode the electrode where oxidation occurs. So you can basically say oxidation occurs at the anode, and reduction occurs at the cathode. The way that I remember these, and it's not very pretty, it's one of those things where you kind of say it and then you look sheepish, is I was taught that it's not a ox, it's anox, yeah, good to remember. And for red cat, really morbid, but just think of roadkill. All right, it'll stick in your head, you will remember it. It's a little bit morbid, but it'll help you to remember it. So if we now go and look at those rules, I know over here that the oxidation half reaction is happening. I know over here with the silver, my reduction half reaction is happening. So I can now go and add in additional information and say that at the oxidation half reaction, this electrode is called the anode. So the copper is the anode. Red cat, which means that the silver here, the electrode where that's occurring, is called the cathode. Okay, please note when you do electrolytic cells, you will find that the polarity, the positive and negativeness of your anode and your cathode switch. But the rule that oxidation occurs at the anode and reduction occurs at the cathode never changes. That is a fixed value. All right. So the last thing that we need to do here, or one of the last things, because we've got just a little bit of time, we'll manage to finish this if everybody hangs on, is that when copper turns into copper 2+, it also gives off 2 electrons. Those 2 electrons travel up through the wire, through the voltmeter, which, by the way, we worked out measured 0.46 volts under certain conditions, and then down to here, where those electrons, although one at a time, are gained by the silver plus in order to positive silver. So our rule here for polarity, okay, is the electrode which has an excess of electrons is going to be negatively charged. So our anode is the negative electrode. The electrons are going to move from the negative to the positive. So our cathode here is the positive electrode. So these follow the same rules in voltaic cells as they do for anions and cations. Anions are your negative ions, cations are your positive ions. So we've got a spontaneous reaction here where copper wants to give away electrons and silver wants, well, silver plus wants to gain electrons. So because this is spontaneous, by us keeping the two half reactions separate, sorry, I don't know if someone's got a question.
Yes, ma'am. Sorry, ma'am. Please, can you please repeat what you said about electrodes with excessive electrons and then...
Oh my goodness, sorry. Guys, I had my screen frozen. Been drawing quite a lot here without you being able to see. Please always correct me. Sorry, sometimes it does happen. All right, so can everybody now see all the little scribbling that I've been doing without you? It may have been for a little while. How long have I been doing it for? Hopefully not that long. I think it was since I went and checked the silver. All right, so maybe 2 minutes. Please, as soon as I've done, somebody just shout at me because it does sometimes happen and I haven't remembered. All right, so here you go. You've got a beautiful screen here with everything that I've been drawing. Okay, so we have, I don't know when I last you, anox, red cat. So the oxidation occurs at the anode, the cathode is where reduction occurs. If you look at my pretty picture, there's our copper going to copper 2 plus, our silver plus depositing as silver. All right, there's the anode being positive, sorry, the cathode being positive, the anode being negative. I told you that the copper goes to give us copper 2 plus and 2 electrons. There's the copper 2 plus, there's the 2 electrons. They go around through the voltmeter, which has a reading of 0.46 volts. Down to the other side, the electrons join with the silver plus to deposit as silver. Okay. Is there anyone who I've lost any of these bits on? I'm sorry. Sometimes it does happen. You do need to shout loudly so that I realize. Okay,
Excuse
brilliant.
me, ma'am.
Yes?
Ma'am, for the polarity, is that what ma'am just said now?
Yes. So the polarity comes from the fact that this reaction over here, which is our oxidation half reaction, produces electrons. So the electrons are going to leave the copper electrode and go to the silver electrode. Because there's an excess of electrons, that will make copper our negative electrode. And if you remember, anode, anion is negative, okay? So the electrons will travel around the external circuit through the voltmeter to the other electrode over here. And when they arrive here, the electrons will effectively be going towards the positive. The silver plus deposits with the electrons to deposit a layer of silver on the outside. Does that make sense? Okay.
Yes, ma'am. Thank you.
Now, if you look at this, we've almost got a complete path for the electrons to travel through. So what I was saying here is we will have copper spontaneously giving off electrons and silver plus wanting to gain those electrons and effectively form silver. So the reason that we have to keep these two half reactions separate from each other is that if we didn't, the electrons would just be transferred from the one substance directly to the other, and we wouldn't be able to make them run through our external circuit and do work for us. So whenever we're dealing with a voltaic cell, we keep our two half reactions completely separate from each other. All right, does that make sense? Okay, I'm hoping that that's everybody saying yes. All right. Okay, so the place that I got the voltage from is, if you remember, I did that E theta cell calculation on the previous example. That's where it comes from. Please don't stress. I'm trying to do a lot of this very quickly. I'm probably going to slow down and rather do it properly. But I promise that we'll go through the E theta cell in detail in the next lesson on Thursday. All right, I just need to quickly finish this up, or otherwise I'm going to have a little bit of a problem with putting it all together. So what completes this circuit here is something called a salt bridge. Okay, So as soon as we have got a salt bridge, the salt bridge completes the circuit. Typically in a salt bridge, we usually have potassium chloride. But I'm already warning you that because of the fact that I've used silver plus here, I cannot use a chloride. The chloride will effectively form a precipitate with the silver, so I'm going to use a way safer salt bridge, which is potassium nitrate. Potassium nitrate can be used for any cell and it'll never not work as a salt bridge. Quite often they tell you potassium chloride, but a chloride cannot be used with silver or it'll precipitate. Precipitate means the silver and the chloride join together, and they crash is the wrong word because you guys won't understand it, but as a solid, they leave the solution and we end up with absolutely no electrolyte left in solution. So what will happen here within the salt bridge is effectively we won't just have Ag plus and Cu2 plus. We'll actually have a solution. So this won't just be copper 2 plus. This here will usually be copper nitrate. Okay, so we've got to have a source of copper 2 plus, but it could be copper nitrate, copper chloride, any copper electrolyte. Over here, this won't just be Ag plus. This will be AgNO3. And what will happen is as the silver is continuously depositing, in this particular solution, we will end up having an excess of nitrate. Okay, so we'll have extra nitrate because the cation keeps depositing on the cathode and the nitrate is left behind. On this side, what's going to happen is we're continuously pumping out copper 2 plus, which means on this side, we will have a shortage of NO3 minus. So since we have an excess of nitrate and a shortage of nitrate, what logically happens here is through the salt bridge, the electrolytes balance themselves out. So what I used to think, and it helped me a lot when I was younger to imagine happening here, is what actually happens, or what I used to picture, was the nitrate goes zips through here to the other side. And when it does, it carries a negative extra electron with it. So I could picture in my head that the electron went the entire way around the circuit. This little bit, it got a piggyback on the back of the nitrate, and we had a full circuit where the electrons were able to travel. What I now know is that it's a little bit different. We instead don't just have the nitrates moving on their own, but what can happen is also that some of the potassium will move this way to balance out and add in, wait, the potassium, no, wrong way around. The potassium can move that way, so it can effectively replace the silver plus that's been lost. So it can put extra positive ions on this side. And what also happens is whatever anion you've got there can move through that way. All right. So ladies and gentlemen, this is the starting idea of how a voltaic cell works. I'm going to just quickly wrap up because we've got about 2 minutes left and I don't want to leave anybody dangling too badly. I promise we will be continuing with this again on Thursday. There's still a little bit of like loose ends tying up that I need to do, but hopefully you all get the general idea that you're going to have 2 half cells. In each half cell, you're going to create either an oxidation half reaction or a reduction half reaction. One side loses electrons, one side gains electrons. Because of the fact that we've got everything that we need to read the half reactions from left to right or right to left, we are guaranteed that we can form a spontaneous reaction where the oxidation half reaction is above the reduction half reaction. I used to tell, well, still do, my students that if it forms a C, like you'd normally write a C, not like people who write weird C's do, if you form a spontaneous C, it tells you that the reaction is spontaneous, and therefore we are effectively turning chemical energy into electrical energy, which is our flow of electrons. Okay, so chemical energy into electrical energy. That electrical energy is created because your oxidation half reaction, or your cell that makes your oxidation half, wants to lose electrons, and the other side, your reduction half, wants to gain electrons. A salt bridge has a function of completing the circuit. So it allows the electrons or the charges to go the whole way around the circuit. So the salt bridge completes the circuit. And the second function of the salt bridge, we say, is that it maintains electrical neutrality. Now, by maintaining electrical neutrality, it ensures that this solution doesn't become too positive because of the buildup of copper 2+ and the shortage of whatever your anion is here. And this side doesn't suddenly have a shortage of positive and become negative. So we don't end up with one half cell being positive and one half cell being negative. That is not the same as your electrodes being positive and negative. I'm talking here about the electrolytes. So it allows us to effectively have the ions in the salt bridge move to counteract that. So the positive ion will move into the solution that would otherwise become negative and make it stay neutral. And the negative ions move into the solution that would otherwise become positive and make it neutral. So effectively, we end up with a solution where electrons are flowing, okay, spontaneously, and therefore we are creating an electric current. It is possible for us to work out what the voltage is under certain conditions. Those conditions, and this is where I'm finishing off today, are called the standard conditions. And in the standard conditions, our temperature is 25 degrees Celsius. Our concentration of any electrolyte here is 1 mole per decimeter cubed. And the pressure of any gases, we haven't really had examples with gases, but we will get there. The pressure of any gases is 1 atmosphere or 101.3 kilopascals of pressure. So this idea is the starting point that we work from. What I'm going to ask you all to do, just to brush over before I see you again on Thursday, is I want you to try to commit to memory. Oil rig, oxidation is loss of electrons, reduction is gain of electrons. The fact that the reducing agent is oxidized and the oxidizing agent is reduced, and the fact that oxidation occurs at the anode and reduction occurs at the cathode. All right, if you are able to do all of those things, then you're in a very good